Perfect. We have a nice definition here. The definition says, well, here, if F is continuous vector field, F is a continuous vector field defined on an oriented surface like S, which is defined on an oriented surface like S, and it has a unit normal vector like N with unit normal vector N, then the surface integral of F is defined this way. The surface integral of F on S is double integral of F dot ds over S, which can be written as the double integral of actually F dot N ds over S. So guys, note that I'm just bolding this letter S here, and this letter here is not bolded. This integral is also called the flux of F across N. It's called the flux of F across S. Okay, let's take a look at one example to see what's happening here. Example. Find the flux of vector field F, which is defined to you as Z, Y, and X across the unit sphere. Unit sphere. Very good. So we have a nice formula to follow. We know that we need to compute the double integral of F dot ds over the unit sphere, which can be calculated using the double integral of F dot N ds. So first of all, we need to come up with ideas how to calculate N, all right? Remember that N in parametric form is actually just RU cross RV, and then you do the computation. So since we have a nice parametric form for a unit sphere, we're going to use that. So take a look at this. We call that R of phi and theta is equal to, from what you learned, is sine phi cosine theta, sine phi sine theta, and eventually you have cosine phi. And since it's a unit sphere, your phi is bounded between 0 to pi, and theta is in between 0 and 2 pi. Very good. We can substitute everything that we have in F and write F in terms of phi and theta. And recall that from what we did, our phi cross our theta, we don't know, do the computation again. We already did that. You already saw this, which is equal to sine squared phi cosine theta and sine squared phi sine theta and sine phi cosine phi. I already computed this for you. Well, we want to know what is f dot n, all right? Okay. So to do that, I need to write f in terms of phi and theta and do the dot product. F of r and theta can be written as, well, here you have your z, which is nothing but cosine phi. And then you have your y, which is your sine phi sine theta. And you have your x, which is sine phi cosine theta. Now let's do the cross dot product between these two. We already did the cross product here. So f of r and theta, just make sure it's bolded so you know we are working with a vector function. Dot, here we have r phi cross r theta. Okay, let's see what do we have here. Cosine phi, sine phi, sine theta, and sine phi, cosine theta, dot sine squared phi, cosine theta, and sine squared phi, sine theta, and sine phi, cosine phi. Very good. So we're going to multiply the first components. We have sine squared phi, cosine phi, and cosine theta plus. Now the second components. Here we get sine to the third phi. Then we have sine squared theta plus, now the last components, here we have sine squared phi, cosine phi, and cosine theta. Very good. Can we simplify this? Well, we can simplify this by, but let's just put that into the formula. The double integral of f dot ds is equal to the double integral. So we're going to have this. Here you have sine squared phi, cosine theta. So you can end up with two of these. So we have 2 sine squared phi, cosine theta plus sine to the third phi and sine squared theta. And here you have, for example, d phi, d theta. The rest is just doing the computation for your integral 0 to pi, 0 to 2 pi, and then you can start taking these integrals. Perfect. We can separate these two and then take in the integral by separating them as well. So here you have integral 0 to 2 pi, 0 to pi, 2 sine squared phi, cosine theta, plus the double integral 0. Forget to write down d phi, d theta, plus the integral 0 to 2 pi, 0 to pi, sine to the third phi, sine squared theta, d phi, d theta. Very good. So let's see what we have here. We can use Frobenius theorem, right? Because there is no connection between these, there's no addition, subtraction. So this guy can be written as integral 0 to 2 pi, cosine theta, d theta, multiplied by integral 0 to pi, and you have a 2, so let's write down 2 in front of it, sine squared phi, and cosine phi, then d phi, plus integral 0 to 2 pi, sine squared theta, d theta, multiplied by integral 0 to pi. And here we have sine to the third phi d phi. A lot of elementary integral for you involved here. So remember that when you're taking the integral of cosine theta between 0 and 2 pi, this guy is going to be 0. 0 times this integral gives you 0. So you can just easily, without calculation, just get rid of this integral and just focus on computation here. This becomes the integral 0 to 2 pi and sine squared theta d theta, and here you can use u sub because it is integral 0 to pi, and you get 1 minus cosine squared phi times sine phi d phi. And as you saw before, you can do the computation and you can use half angle formula here, and the final answer should be equal to 4 pi over 30. The use of formula for oriented surface to do the computation for your flux. So if I ask you to find the flux of a vector field over an oriented surface like a unit sphere, we're going to follow the formula, convert everything back into, if you have a nice relation between x, y, and z, use it. If not, you have to find parameters to rewrite this in parametric form.